To properly explain fraction multiplication, I want to give you an example question that we're going to do, but first I'd like to take you back a step to adding fractions. Because when we add fractions, we need to make common denominators, and a lot of people get confused when they multiply fractions, thinking that they still need to make common denominators. So let's just have a little look at why you need to make them when you're adding, but you don't need to make them when you're multiplying. When you're adding something like 2/3 and 3/4, you can imagine it as adding pieces of pizza, if you like. We've got 2/3 here and 3/4 here. Now, how many pieces of pizza have I got? I've got 5 pieces, but they're not all the same size, are they? So it's almost like I'm dealing with two different currencies here. Imagine adding US dollars and Australian dollars. You've got a lot of dollars, but you can't quite work out what you have unless you convert them both to a currency where they're equal and they can be added. So when we do a question like this, we turn them both into twelfths because thirds and quarters both communicate well with twelfths. We can divide up these quarters into 3 pieces each, because if we had 12 pieces of pie or pizza, having 9/12 is the same as having 3/4. And if we divide these ones into 4 pieces each, that too would make 12 pieces of pizza in the whole circle. And having 2/3 means having 8 out of 12. So we have 8/12 plus 9/12. Now they're in the same currency. They can speak to each other, and we know that we've got 17/12, which you could always convert to 1 5/12. Now this picture makes sense for this problem, but we need a different picture if we're to understand multiplying fractions. And the picture that I want to take you back to is the first picture that you would have imagined when you first learned how to multiply. Now, when your teacher in probably year 1 or 2 taught you about multiplication, they probably drew something like this that had 3 rows and 4 columns. And you learnt that 3 rows of 4 or 4 rows of 3 is 12, and it sort of looks like this. And even when we do any multiplication problem, we sort of conjure up a picture like this in our minds, potentially. Also, this helps us understand calculating area when we know that multiplying the number of blocks on one side by the number of blocks on the other side, multiplication gives us area, and we're really used to doing this. Now, what we're going to do today is use the exact same picture, but instead of 3 times 4, I want you to think about doing thirds times quarters. Now, if this length here was one of something, 1 kilometre, 1 metre, one of anything really, 1 unit, then what I've divided it up into here is really thirds, isn't it? And if this whole side here could be said to be 1 of something, 1 metre, 1 unit, whatever you like, I've divided it into quarters, haven't I? So if I want to multiply 2/3 by 3/4, I'm almost doing 2/3 of. Remember, back in year 2, you used to use this word and say it's of, 3 groups of 4. Well, we have 2/3 of 3/4. Now, taking a couple of different colours here. If we want to shade 3/4 of this picture, it's pretty obvious that we'll need to just shade 3 out of the 4 columns. Everyone happy with that? I've shaded 3/4 in purple. Now, if I'm going to shade 2/3 of the whole area, I've got 3 rows, so I can just very easily shade 2 out of the 3 rows. Now, 2/3 of 3/4, well, here is the whole 3/4, and here is 2/3 of it, okay? The other way you could look at it is if we were doing 3/4 of 2/3, you could say here is the whole 2/3, this part, and this part here is just 3/4 of it. So the area that's been shaded twice, let's colour that in, that's going to be basically the visual representation of our answer. Now, the total number of boxes here is 12, and that makes sense because it's always going to be 4 times 3. If I divided this up into fifths, I'd have 5 boxes here, wouldn't I? So the number of boxes altogether is going to be the denominator times the denominator equals the denominator of the answer. And the number of boxes that I've shaded twice, well, this box is 2 tall because this number is 2, and it's 3 wide because this number is 3. 2 3s are 6, so I really just need to multiply the top by the top to get the top. Now you might say, hold on a minute, 6/12, that's not the best answer. 6 out of 12 is the same as 1 out of 2, or half. Now let's look at a couple of little tricks. We've got the picture here to understand why this works every time. Now we need a couple of tricks so that when we multiply, there's nothing wrong with doing top times top equals top, and in fact we should remember that. Let's write it down. Top times top equals top, and bottom times bottom equals bottom. Now I could have written numerator and denominator, of course, but let's try and use words that are going to stick in your mind and you'll remember them your whole life. That recipe works, and it gives us an answer that is correct, even if it's not in its simplest form. Now you can use that method and then cut down that answer and simplify it till you've got the best fraction possible. You could also do some cancelling along the way. Now let's have a little look at how cancelling works. If I have 2/3 times 3/4, I'm going to, on the top, have 2 3s, aren't I? And on the bottom, I'm going to have 3 4s. I've really just put an extra line of working in there to show how I'm going to get my 6/12. Can you see, though, that if the 3 and the 2 were round the other way, it really makes no difference where they go, because 2 3s is the same as 3 2s. So these numbers could switch places quite easily, as could the numbers on the bottom. So what that means is that effectively, any number on the bottom can cancel with any number on the top. So just as you might be used to seeing a fraction like 4/8 and saying, oh, when I first learned how to cancel, I divided the top and the bottom by the biggest number, the biggest factor that they both shared, and so then I got my answer that 4/8 is equal to 1/2. As you get a little bit better at it, a quicker way to do it is just to say, hey, 4 and 8, they're both in the 4 times tables. I can divide this by 4 and just do it in your head and replace it with the new number. And divide this by 4. Do it in your head and replace it with the new number. Then you can write your answer out all nice and tidy. So we know that we can cancel top and bottom of a single fraction. So if we had a number here that was, for example, let's say 6/8, we could say, hold on a minute, these are both even numbers. I can halve this one and halve this one, couldn't we? So we can see that we can cancel within a specific fraction. But we can also cancel diagonally. So the 3's are both in the 3 times tables, and the 2 and the 4 are both in the 2 times tables. And because they're both going to end up on the top anyway, whether they're here or here, and they're both going to end up on the bottom anyway, whether they're here or here, it explains why we can cancel a number with the number directly below it or the one that's diagonally opposite. Never the tops and the bottoms, though. It has to be something on the top with something on the bottom. So the quick way to answer a question like this is to do your cancelling first. That way, when you do top times top equals top, bottom times bottom equals bottom, you'll get the best possible answer straight off. You're also dealing with nice small numbers. So 3 and 3, they can both be divided by 3, can't they? Giving us 1s. And 2 and 4, we can halve both of those. Halve this one and halve that one. Now we have 1 times 1 equals 1, and 1 times 2 equals 2. Let's look at one more example where we can do this cancelling so that we can get our best answer nice and easily. If we have 2/7 times, what should we do? 21, should we have 20ths? All right, we could do 2 21s is 42 and 7 20s is 140, but then we've got some really big numbers that we have to cut down at the end to simplify. Much easier to look for some cancelling first. I've straight away spotted that the 2 and the 20, they're both in the 2 times tables, so I can halve both of them. Divide this one by 2, divide this one by 2. Now the 7 and the 21, they're both in the 7 times tables, so I can divide this one by 7, and I can divide this one by 7. Now I can apply my recipe to get the answer. No need for common denominators. Top times top, 1 3 is 3. And 1 lot of 10 is 10. 3/10 is the best answer. I can tell this because neither of these share a common factor. So I've got a good answer really quickly and easily.